This endpoint queries a PostgreSQL database, which joins 5 tables and runs a window function across every country in the Chinook database. The payload size is roughly 92 kilobytes. Watch the response time. Now watch what happens on the second request. Same data in around 7 milliseconds. No Postgres was harmed. That's Redis, and in this video, we'll know exactly how to implement this. So what is Redis? Redis is an in-memory data store. Everything it holds, it lives inside RAM, the primary memory, and not the disk. And this is precisely why it is this fast. Generally speaking, your application is going to talk to a relational database, for example, Postgres or SQL Server, depending on your case. And while this relational database is really powerful, it is better utilized doing the real work. For example, reading millions of rows from the disk, generating plans, executing queries, joining tables, and things like that. So what Redis does is sit between your application and the database, and your app asks Redis for the data first. And if the data is available, we call that a cache hit. Redis will return it instantly and your database is going to chill. But if the data is not available, cache miss, we go to Postgres, we query the data, and then we hand it to Redis to remember it for the next time. And once that is done, we will return the response to the client. On the subsequent request, like we saw earlier, the backend is going to just return the cached response. That's it. That's the whole idea in a simplified manner. Before we touch any code, let's take a look at raw Redis on the terminal. Now before us, we have got the three most useful commands on Redis: the set, get, and delete commands. And these alone can carry you, or at least they are carrying me. So let's run our own Redis server on Docker, and you can follow along with me if you like, and let's play around with these commands a bit. So we'll set up a Redis container first. So the P flag here is just going to map the ports, and the reason I'm choosing 8.6 Alpine is and not latest is to prevent surprises later. So this will download an image for us and create a container, and once that is done, we can just start executing commands on it. So we'll run Redis CLI on this one, and now we are inside our container. So let's see some of these commands in action, right? So we can go ahead and try to set name as Johnny, and it returns OK. Similarly, we could set something else, for example, food as sugar, and we can also try to retrieve these values, and if we write get name, we get back Johnny, and then we could possibly delete them, and if we write delete name, it returns integer 1, and if we try to get that key again, it returns nil. Now one of the things that you will come across very frequently is to set keys with a time to live, or TTL. So what that means is that key will be available inside Redis for a certain duration of time, which you will specify in seconds, and after that it will be gone. So let's see how we can do that. So if we go ahead and set trending as maybe Linkin Park, and specify the expiration duration or time to live in seconds, let's say 5, it returns OK, and we try to get trending back, it returns Linkin Park. But after 5 seconds, if we go ahead and do that again, it returns a nil. And this will be really useful to invalidate the stale cache from our Redis server. Depending on your use case, you may be using more complex cache invalidation techniques like the cache aside pattern, where we invalidate the cache on writes, or event-based cache invalidation. All that depends on your specific use case, and this one is the simplest one that we can start with. Okay, now let's take a look at our infrastructure. We are already aware that we have got an Express app, a Redis server to cache the frequently used data, and a Postgres database. Let's take a look at the Docker Compose file which is behind it. Each Compose file starts with a top-level services definition. This block defines what containers exist in our Docker network. So I'll go through some of the important configuration here. Take a look at Redis DB and Postgres DB. Docker Compose will automatically register these service names as DNS entries on the internal Docker network. So what that means is the containers inside the network will be able to reach each other using these names. But this also means that the services outside the network will not be able to resolve these host names. So if you're using some kind of managed database or cache, just go with your connection string, leave this. Next up, we have got the container name. And be careful here because I tripped here a lot of times, that this is just a human friendly name that appears each time you run docker ps to check the status of running containers on your computer, or maybe when you run docker exec to fire off one of commands. But it is not something that you will use to connect your backend to the Redis server or the Postgres server for that matter. The restart key specifies here that each time your computer is shut down, or maybe the container itself crashes for some reason, Docker will always try to bring it back up whenever it possibly can. So you don't have to come again and run Docker Compose up. It will always keep running unless you stop it. The port key is the standard Redis port mapped to our computer. Now the volumes key. So I'll come down to Postgres here because that's where it is really important. And the reason it is really important is because this is specifying the exact path in our computer where Postgres data will be stored. Otherwise, whenever the container is down, all our data will be wiped. So let's go to our root directory, specifically the path var lib and docker. And if we try to list down what we have here, we can see that there is a volumes folder. If we cd into it and try to list down what we have got for our app here, we can see that there are two folders, one for our Postgres data and the next one for our Redis data. This is where the data of our container that is supposed to be persisted is available. So let's go inside the Postgres folder and inside its data, and if I list everything here, you can see that these are all the internal files of our Postgres database. Anyway, one final thing I want to note here is the use of the environment key. And this is how we inject secrets into our Docker containers. By default, Docker is smart enough to pull these from the .env file. And the reason we do this is because Docker Compose is something you may want to commit to your Git, right? And you don't want to commit secrets inside this file. Now let's take a look at how we can use Redis inside our application. For this, we are going to be using IO-Redis, which is the most popular Redis client for Node. So now I'm in my VS Code, specifically the config folder of our Express app. And here in this Redis file, we are going to configure IO Redis to talk to our Redis server. So let's start by writing down all the necessary imports. So the Redis class from this IO Redis package is the one which is responsible for both creating and establishing the connection. So first thing that we are going to take care of is to create an instance of this class. And we are going to supply in this constructor two arguments, that is the Redis host and the Redis port, and both of them we are going to grab from our env file. There are some other things that you can provide in this constructor aside from these two. For example, retry strategies or password in case you have authentication enabled in your Redis. But right now these two will serve us fine. And we are going to set up two basic event listeners to log the status of our connection. So let's do that. And the idea with this Redis client is that we are going to export this as a singleton and we are going to reuse the same connection throughout the whole application. So what's that going to do is going to prevent the exhaustion of connection limits. So we'll add one more line here to default export this client. We are done with our Redis configuration. Now let's try to understand how we are going to use it inside our Express app. For that, let's briefly try to understand how the backend is scaffolded. So we are calling the Express function to create the app. Then we are adding the JSON parsing middleware on top of it, and we have got just one router, which is the leaderboard router, and we are mounting it on the leaderboard path. There is a simple health endpoint which returns a simple up on HTTP GET. Finally, the server is grabbing port from the environment variables, and inside the callback function we are simply logging on which port the server is starting. Fairly common setup. So let us try to go inside the leaderboard router and see what we have got there. So here we have got just one endpoint, which is the top artist per country, and this is the exact endpoint we saw in the beginning of the video. So let's go inside the controller. Here we can see that the controller is simply just a try-catch wrapper over the service function. So we'll go into the implementation of the service function to try and understand what exactly that we are trying to cache here. Before we move on to the query, I'd like to show you this awesome tool that my friend told me about. So earlier I used to work on SQL Server, and there I had to install SSMS, and with Postgres you have to install pgadmin for your SQL client. This means that depending on your project's database, you have to get used to different interfaces and authentication styles of various different SQL clients. Plus, some tools like SSMS are Windows only, whereas dbeaver has got a binary for most operating systems, including a Linux version. You can download this for yourself by going to dbeaver.io. Next up, you can go ahead to this link on GitHub to download the Chinook database, which is the basis of our query. You can refer this README file to download the SQL script for your preferred database. One small setting I'd like you to change in dbeaver. Go to Window, Preferences, and under SQL Editor, go to SQL Processing and change this specific setting. Blank line is statement delimiter. It will be set to always by default, but choose never and click apply and close. This will fix the terrible IntelliSense it has for CTEs. With that out of the way, let's try to get a surface level understanding of what we are trying to cache. I have divided this into two CTEs and then a select statement, and let's try to go one by one on all of this. Now to reach our goal, we need to find artist's revenue. The revenue here lives inside invoice lines, and to get the revenue of each artist, we need to traverse the whole music store schema. Each invoice line has a track ID as foreign key, and that track is linked to an album. And through album ID, we can reach the artist. And this is essentially what the first CTE is doing. So each invoice is sort of like a bill, and an invoice line is like an atomic entry inside that bill. So if I just execute our first artist line revenue CTE, what we are getting in result is essentially the name of the artist attached to each invoice line. Next, in our second CTE, the artist country revenue CTE, we are taking the raw revenues that we got from the previous step and we are grouping it by artist and country. Notice that we have joined the invoice table here because only the invoice table has the information about billing country. So this is the fifth table that we are joining. And if I try to select the data that we have got until now, we can see that we have now got the artist, the billing country and the total revenue inside that country. At the end, we are using row number on this intermediate result to get the top n, in this case top 100 artists by revenue on every country. The partition clause here means that the ranking will reset on each country and the order by simply ranks the artist in terms of descending revenue. So we get the highest earners first. We are getting the top 100 artists because Billboard style. Having understood the query, the service layer feels a lot more approachable now. First, we set up a specific name for the Redis key to reflect our use case. Next, each time a request comes, we first check Redis if it has got some value stored against that key. If so, we will simply return that data and not touch the database. If not, we query the database, then store the result in a variable, and finally, and this is important, we store the result against our Redis key for using next time. 1800 here is time to live and that amounts to 30 minutes. Once done, we return the data. So let's put a breakpoint here on line 13 which returns the cache data from Redis if we got it. Another one here on line 58 which queries the database in case we didn't, and another one here on line 64 which sets the Redis key after querying Postgres. We will also remove any existing keys from our Redis server by running flush all. And now let us head to Postman. We will send a GET request to our endpoint and we can see that the debugger has jumped to line 13. If we hover over cache data, it is null. So if I hit play here, it will jump to line 58 as expected. And once the data has been queried, it will jump to line 64. It sets the Redis key, and if I hit play again and come to Postman now, we can see that our result is now here. If I go on and click send again, the debugger once again has paused on line 13. But this time if we hover over cache data, we can see that there is a lot of data inside there. So if I click play once again, this time the database remains unbothered. And for the subsequent returns, until the cache is invalidated either via time to live or some other way, the application will rely on cache data. To recap what we did, we took a slow endpoint powered by a relatively stable and non-transactional query. We added Redis to cache the results, and subsequent requests bypass the database entirely. The takeaway here is simple. We reduce the database load by adding a caching layer. Thank you for your time and I'll see you later.